Good morning. This is Zhipeng, a PhD candidate from Washington State University, and my advisor is Dr. Xianmin Shi. So today, it's my pleasure to be here to introduce our recent research work. The title is The Effects of Nanomaterials on Engineering Performance of a Siliconate-Based Sealer for Cementitious Composite. Here is the outline. First, I'd like to introduce some background and our hypothesis, and then the experimental program and our result, and then summarize our future work. Surface treatment is important for concrete, and it's an effective strategy to protect concrete from freeze soil damage and soil scaling damage, and then extend the surface life of concrete infrastructure, the pavement or bridge decks. So based on their function, the surface treatment can be divided into three types. The first one is barrier coating. For example, the epoxy. So for this kind of epoxy, it will form a film on the surface and then keep the water out. The second is called hydrophobic impregnation. For example, the thinning and the siloxane. For this kind of sealer, it will make the surface hydrophobic and then make the surface hit the water. The second one we call is pore blocker. For example, some silicate. For those kind of sealer, it will generate some gel product on the surface and block the pores and then hinder the transportation of water in the matrix. Of course, some sealer plays all of those three roles, and here we introduce a promising candidate, the potassium silicate, PMS. And so PMS will react with the airborne CO2 and generate a compact film on the surface, and then provides the substrate with the hydrophobic film, and then it reacts with the CO2 and generates some products. For example, the potassium carbonate, and blocks the pores. So this one is very promising. Recently, some research developed the research of nano-modified sealer, as Dr. Peng Ho introduced earlier. So, for example, some nano-silica or nanoclay will enhance the performance of sealer. So based on those research and our previous foundation, here we choose two foldable nanomaterials, the nanoclay and the graphene oxide, to enhance the performance of this PMS sealer. This is the structure of nanoclay and the structure of graphene oxide. Here is our hypothesis. First one, the graphene oxide and the nanoclay will modify this sealer and generate a micro-nano roughness to improve its hydrophobicity. Second is that the reactive nanoclay will react with this alkaline PMS sealer. Due to the hypotonetic reaction, they will generate KASH gels. Nanoclay provides the alumina and the silica, and the PMS sealer provides the potassium and the alkaline. And graphene oxide is amazing. It will accelerate the hydration of cement. So here we also hypothesize that graphene oxide will catalyze the process in hypothesis 2. And here is the materials, the properties of materials that we used in our research. The dispersion of nanomaterials is usually a problem. So to guarantee the well dispersion, we use this ultrasonic facility for 30 minutes to disperse the nanoclay and the graphene oxide in PMS sealer. First, we introduce different dosage of graphene oxide into this sealer, and then we test the water contact angle. We choose the best one, and then we introduce nanoclay. And the number here means the dosage of different nanomaterials. For example, the 50N and the 6GP means the PMS sealer contains 0.15% nanoclay and 0.06 graphene oxide. These are the tests we conduct in our research. We test the water absorption, gas permeability, and the water contact angle. We also test penetration depth and the viscosity, and the soil scanning resistance. Here's other results. These two figures summarize the water contact angle of all the samples. The PMS sealer contains 0.50 nanoclay and 0.06 graphene oxide, shows the best performance. And we can learn from this figure the water contact angle test. The figure is almost hydrophobic than original long-modified surface. Oh, just mentioned, we did this test on a glass plate. We didn't use the mortar sample just avoid the influence of pores to make these results more reliable. And here we summarize some our assumption and the mechanism of this increased water contact angle. So the figure A and B demonstrate the original mechanism of PMS sealer. It reacts with react with the airborne carbon dioxide and then dehydrate and generate this guy. And this guy connects with the concrete matrix in two modes, and it changes the surface, changes the function group on the surface, and then make it hydrophobic. This is the original mechanism. So after adding nanomaterials, we summarize that some nanomaterials react with the air-climb PMS sealer and then generate some large gel, and it generates this kind of micro roughness. For those nanomaterials didn't involve the reaction, and they generate the nano roughness. So for this kind of nano micro hybrid roughness, they will make the surface more hydrophobic, just like the leaf of lotus. Here is the water absorption behavior of our mortar sample coated with different sealers. And we also find that this guy makes the decrease the water absorption coefficient greatly. And compared with the non-treated mortar sample, it's decreased about 30%. And compared with the original PMS sealer, it's decreased about 31%. So for this decrease, we attribute it into two reasons. The first one is that the surface changed. So, the more hydrophobic surface, the less water absorbed. And then the pore structure was blocked by these nanomaterials, and it's made it harder to absorb water. And the result of gas permeability is as similar as the water contact angle, water absorption behavior. And the main reason might be due to that this nanomaterials or its hydration products block the pores. And gas permeability is also an important performance. The air, the CO2, and the oxygen and the moisture vapor usually will reduce repercussion risk. Here is the soil scanning resistance. The result is obvious that the PMS sealer with this nanomaterials decrease the mass loss greatly. Here we test the roughness of the surface, and the darker color means the deep scanning. So we collect some data, and then we summarize in this box plot, and we find the mass loss was positively correlated to the scanning depth. And for the long-treated, the original mortar, the mass loss is obvious. But so after adding nanomaterials, then the mass loss is not obvious. And one more interesting thing is that So after adding nanomaterials, the variance decreased. We can compare the length of this box, of this yellow guy and this red guy. That means, nanomaterials play some fantastic roles. And so far, everything looks well, but however, we also find some potential problem that adding too much nanomaterials will result the increase of viscosity. That means it's very hard to make the sealer get into the concrete. In addition, the penetration depth was also decreased. So for original PMS sealer, its penetration depth was about 3.3 millimeter. However, after adding nanomaterials, it's decreased. So this too is not a good signal, and this is it's not a good signal, and this also our future research to find a way to balance this performance and the previous engineering performance. Here we develop a model to say the relationship between different parameters, and we find decreased gas permeability and increased water contact angle together will generate a lower water absorption coefficient. However, so this is a prelim model, so we need more data to fit into and get a more reliable result. Here we also run the thermometric analysis to say what's going on under this condition. And we find for this yellow curve is PMS sealer with nanoclay in 20 days. And we find it looks like the cement or the TGA result of cement. So is the main decarbonization during the first range is KASH, but for the other sealer is the decarbonization of KHCO3. This means for the longer time, and the positive reaction is more obvious. Okay, so this is also a prelim analysis, and more fundamental research is needed to figure out what's really going on. Here is our summary. First, nanomaterials can help enhance the engineering performance of sealers. However, it can help to enhance the hydrophobicity and refine the pores. However, we need to find a balance between those the dosage and the engineering performance to avoid the bad penetration depths. For our future work, we may move to the concrete material industry and its long-term performance and optimization, and optimize the dosage of nanomaterials, and then its life cycle assessment. And so this project was funded by National UTC, and thanks for donating our materials. And this technology was filed by the provisional patent was filed by WSU Office of Commercialization. Thank you. Any questions?